Hello, thanks for the introduction. I would cover two separate topics, post-quantum blockchain and zkTLS. First, let's look at what a blockchain should look like in the post-quantum era. So, how to define cryptography? Informally speaking, cryptography is about constructing and analyzing protocols that can prevent adversary from reading and intercepting private messages, where we care about various information security properties, such as integrity, authenticity, confidentiality, right, non-repudiation. And this was achieved by applying the corresponding cryptographic algorithms or protocols, such as hash functions, digital signatures, zk, which are all essential to blockchains. And we also have TLS. So the security of a cryptocurrency, such as BTC, ETH, or any coin, you name it, crucially relies on the underlying security of these various cryptographic algorithms used, such as digital signature and hash functions. And underlying every digital signature which is used in blockchain, we have the ECDSA, EDDSA, or BLS. Or they all depend on the same mathematical problem, which is called ECDLP, which is the discrete logarithm problem over elliptic curve, right? Which is not quantum secure, because in the 90s, Peter Shaw invented a quantum algorithm which can efficiently solve ECDLP. So if a sufficiently powerful quantum computer is invented, then all the blockchain can be broken, right? And there are very optimistic predictions that by the year 2030, such a quantum computer will be built. And we all know that the cryptocurrency addresses, they are the hashed values of the public keys, and by applying hash functions. And even worse, some have their entire public keys totally exposed. According to our survey, nearly 20% of BTC have entire public key addresses exposed to the public. And the case for Ethereum is even worse. It's more than more than 95%. So then post-quantum cryptography comes to the rescue. Despite the name quantum, PQC algorithms, they are still classical algorithms that can run on your devices like PC, laptop, or even IoT devices. And they typically, they provide quantum resistance, meaning that we typically have a mathematical proof. And to be competitive, these algorithms has to be computational and communicational efficient, right? Depending on the underlying mathematical problem they are based on, this PQC algorithm can be categorized as lattice-based, code-based, hash-based, zk-based, and many more. And some of them are broken already. And last year, we know that NIST has standardized 4 algorithms, 3 of which are based on lattice problems, and the other is hash-based. And more recently, they standardized another one which is based on code problems. Actually, the migration to post-quantum cryptography has already begun. The White House, during the Biden administration in 2022, they issued the National Security Memorandum, which sets the year 2035 as the primary target for completing the migration to PQC across all the federal systems in the US. And many major companies are already deploying post-quantum solutions across the diverse platforms and services, such as Google and Amazon clouding service, and the browsers, and the Apple end-to-end secure messaging, and operating systems, and the Starlink satellite communication. So then I would like to present our PQC algorithm portfolio, which aligns with the corresponding NIST standard of proposals. So we have a lattice-based CAM, lattice-based signature, and hash-based and zk-based. And compared with the corresponding NIST proposals, they are more efficient, right? And also our algorithms, they are published at reputable top cryptographic conferences and they are received international recognition. It's not surprising because if you improve on these algorithms, you are doing much better, right? So our lattice-based algorithms, they are like enjoys like 20 or 30% smaller public key size, and nearly 10% smaller ciphertext, or more than 20% smaller signature size. So save the communication overhead. This was published at the PKC 2020. Therefore, because our algorithm is much more efficient, so they are actually the optimization techniques. They are integrated into the final standardized version of this NIST standards, MLKIM and MLDSA. Last year, their designer wrote an article explaining the key concept behind the design, so which confirms that they used our optimization techniques. Then I would like also elaborate on the design of our hash-based PQC algorithm, because hash functions, they are naturally a great fit for blockchains, right? And that's why we focus on optimizing the algorithm. The design of hash function has like a few key components, such as one-time signature, which is only secure for signing a single message, and then few-time signature, which can securely sign more than a few-time signatures, but not many times. Then we would use the Godric tree structure to extend one-time signature to multi-time signature, many-time signatures. And we all familiar with this Merkle tree, which can compress several public keys into a single piece, right? And beyond the design, we also make two contributions. First, we discovered the previous claimed best design of a one-time hash signatures is not secure by providing a forgery attack. Then we also use partial order theory to formally define what a size optimum one-time signature should look like and how to build it. Okay, so it's all about the graph theory. Then this design was published at the top 2 cryptography conference called Crypto. It's not that crypto though. And compared with the NIST standards, our design enjoys like faster signing speed by 16%, and roughly saves the digital signature size by 10%, right? And most importantly, it's the most conservative design, because if you design the digital signature, you most likely will use hash functions to do the compression. So if you only use hash function, then imagine in a world, a very smart computer can break all the lattice problem, code problem, isogeny problems, multivariates, or any other problems. Then this hash-based signature will be the last frontier against quantum computers. So it enjoys the most conservative security. And interestingly, there was this recent paper called hash-based multi-signatures for post-quantum Ethereum by the Ethereum Foundation, where they actually plan to use hash-based signature to replace BIS signature, and our message encoding technique was actually adopted and instantiated in their framework. Okay. And I would also like to mention the ZK-based PQC algorithm, and compare. It's based on the state-of-the-art ZK technique called void in the head, and the hardness is based on like the regular single-room decoding problem. So it enjoys like smaller key size and smaller signatures and much faster signing speed. Right. We also released the first PQC open source library in China. We just visited pqcrypto.dev, right? Where compared with the other open source library called the LIB-OQS. OQS stands for Open Quantum Safe. So compared with lib-OQS, our implementation is roughly twice time faster. Right? And our library also provides a GPU implementation, which accelerates the performance by roughly 2 orders of magnitude. Okay, So then I would like to recall the main theme of this talk, post-quantum blockchain. There are actually two approaches. Either you can build a blockchain system from scratch using post-quantum cryptography solutions. Or alternatively, you can migrate existing blockchains and by adding support for PQC signatures, moving assets to quantum-resistant addresses, and gradually you phase out vulnerable quantum-unsafe signatures, right? But the major challenge is that, like many addresses, they are inactive. So if they haven't been migrated in time, they might be susceptible to future quantum attacks, right? Okay, then I still have some time, so I would like to talk about zkTLS using the interactive ZK. Okay, so zkTLS can be regarded as a ZK extension of the TLS. That's you know that in TLS, the client establish a connection with the server and do the authentication, and he retrieves some messages from the server, right? Then, as the extension, the client proves to a verifier that the message he retrieves is authentic, right? And make a statement about the message. Right? So it has like many real-world applications. A simple one is that I can prove that I have more than some threshold amount of ETH in my, for example, Coinbase account, right? So this concept was introduced about 10 years ago, and we have many solutions like DECO and our approach called the Gabble then proof, which is based on interactive ZK, and which is essentially the special type of MPC protocol. Okay, so TLS, we know that it consists of two phases. In the handshake phase, the two parties, they do the authentication and they negotiate on what algorithm to use, and then it establish a shared key and derive the session key, right? And then in the record phase, they do the encryption, decryption using and authentication using the derived session key. Right? And there are actually two modes for the zkTLS. And in the MPC TLS, you know, the client first do the handshake with the server, and then afterwards, it executes a two-party computation with the verifier to share a session key, and which is then used for decrypting the messages from the server afterwards. Right. At the end, the verifier will prove that he knows the actual key. He can decrypt message and also make a statement about the message in ZK. Right. And in the proxy model, the verifier will act as a proxy between the client and the server by forwarding the traffics, the encrypted traffics between the client and the server. And in the meantime, the verifier should confirm that these traffics either originated from the client or the server. Right. Then afterwards, the client will prove to the verifier that he can decrypt the message, and the message will satisfy some relations. And what's the difference between these two modes? Roughly speaking, the proxy TLS will have a more trust assumption such that you know that the verifier has to ensure the connection to the TLS server all the time, and he should behave honestly. And as a reward, this proxy TLS will be much efficient, since it does not need to run the two-party computation protocol for key derivation and AES. And in our zkTLS, we will use a technique called interactive ZK. So why do we resort to interactive ZK instead of ZK stack? Because you know the key derivation function AES are not efficient when represented as a Boolean secret. So then the ZK stack protocol will have a very high proving time and large memory consumption, especially for clients running in a resource-constrained environment such as browsers. So then our interactive ZK make trade the non-succinctness and trade the succinctness and the non-interactivity for better efficient. So it will have a more computational efficient protocol and with much less memory consumption. And so the interactive ZK protocol is from we use it's called the Quicksilver, which is able to prove trillions of gates with very affordable price and with minimum resources. In this case, we use 2 CPU cores and less than 1 gigabyte memory. Right? And there we did a performance evaluation. And in this case, the clients are located all over the world. And he proved to a verifier, which is located in California, that the data he retrieved from the Coinbase server, which is in yellow, and or the Twitter server, which is in green. And all this can be done, can be completed in a few seconds, like maybe less than 1 second, or in general, it's less than 10 seconds. And in the case of large content proving, it can prove like 20 kilobyte image retrieved from the ChatGPT server in 2 minutes. Right? Okay, so then this MPC-TLS or proxy TLS based on Quicksilver comes with a SDK, which is developed by the Premise Lab. And we also have some recommended best practices, such as the verifier should be geographically distributed near the potential clients to minimize the latency and optimize user experience, and to mitigate the risk of collusion between the client and server. And it would be good to deploy the verifier within a TE. Okay, that's for my talk. Thank you for your attention.